Hello, mic check, sound check. When you can speak, huh? Here is the button.
Just this one.
Okay. Hello, check, mic check.
كم الساعة الآن؟ استوى. شير سكرين. غير من الجسم. بسم الله الرحمن الرحيم. بس خذي الجهاز هذا، خذي الجهاز هذا وشوفي في الصوت. افتحي الصوت هذا. شوفي من خارج.
مفتوح.
بسم الله، تأكدي بس الصوت.
هذا من خارج الجامعة أو في الجامعة؟
No, it is inside the جامعة. بسم الله الرحمن الرحيم. بسم الله. Where is the voice here?
Dr. Saddam, you hear me?
Yes.
Perfect.
But can you hear me, please?
I do.
Huh? شريفة. تسمعي تمام؟
Yes.
متأكدة الصوت ما هوش من هنا، بيجي الصوت من مش عايزين
Right, right.
صح قديش حقها هاي؟ قاسم ما بدي اجيب وحدة.
professor at Texas A&M, and then after that he become professor, assistant professor in 2003 in Qatar. Is one of the founders, one of the 4 founders for Texas A&M University at Qatar. Dr. Wen research interests include neural network, computational intelligence, chaotic dynamical system, complex network optimization and control, smart grids. He has also published several papers in different worldwide reputable journals and conferences. He's also one of the very active researchers in the area of computational intelligence, and he has more than 32,000 citations with each index 91. Dr. Howand also received Outstanding Achievement Award from Asian Pacific Neural Network Society. He is also a Chenjian Chair Professorship. He has also got from the Chinese Ministry of Education Best Research Project Award by Qatar National Research Fund. He's also IEEE Fellow, and he's a Fellow of the World Academy of Sciences. He's a member of European Academy of Sciences and Arts, and academician of the International Academy for Systems and the Cybernetic Sciences. He's a fellow of IEEE in pattern recognition and artificial intelligence, and is also in the Artificial Intelligence Association as a member and distinguished lecturer in IEEE Computational Intelligence Society. His background is mainly mathematics, but his work and practice more in computational intelligence and their application in a variety of applications, especially smart systems, smart grids, and he's one of the well-known researchers in the area. Please join me to welcome Dr. Tuing Nguyen for the presentation on this seminar.
Thank you, Dr. Al-Said, for your introduction and your invitation. It works. Thank you. Thank you. And this morning, I'm so happy to meet several leaders here and get to know more about this university. And before I came here, I checked the internet. I found that this university, that's truly world-class university. But for me, I come from a small city and a small university. So I come from Texas A&M University at Qatar. That's a branch campus of Texas A&M University. Texas A&M University is huge with about more than 60,000 students. But for my branch campus is quite small. We only have like a little bit more than 500 students, including graduate students. And the number of faculty only about 75 faculty. So compared to KFUPM is quite small. But this time is very good for me. I'm so honored to have this opportunity to visit this great university. So hopefully in the future, we have more collaboration opportunities. Of course, before we, I and Professor Al-Said, we have some collaborations like as guest editors for special issue published in journals. I think this will continue going on, and I will get to know more about this university. My background, as Dr. Al-Said said, is mathematics, but my work done in the past 20 years after I moved to Qatar, kind of like a shift to problems in engineering, especially in the very beginning. It's about dynamics of neural networks. So the neural networks, when we form the model for some neural network, that's really like differential equations. And the dynamics, like a stability of the neural network, that's very critical, very important to design neural network. So I'm fortunate and I'm very happy when I look back, I just shifted to the dynamics of a neural network. Then from there, I just gradually expand my research and based on, I say, maybe my group's research to other areas like multi-agent and apply to power grids. So today, I just look at one part of my team's work. We just use the reinforced learning or other computational methods to smart grids. Now for smart grid, this word, that's really like what English implies. So basically, we just try to use the up-to-date the technology, like the sensor or computing technology, to make the power system running smoothly. Ideally, no power shortage, and as another thing, we don't produce much more energy than we are able to consume. And if the power grid with some problems, like this happened about 20 years ago, in the summer of 2003, even though the shortage of the power only like a little bit more than 10 hours, that happened in the northeastern part of US and the southern part of Canada, small area, and for short time. But the economic cost, that's about $66 billion loss for this short time power shortage. And every year in the power system, maybe around $140 billion loss because of the power system not running smoothly. So there are so many problems in this smart grid studying. We want this running smoothly, basically. People studying problems from different angles. Now, for my view, we just try to start from the point of view good for us. So basically, for my team, we are kind of like strong in math. Of course, my team, almost all of them, they are research or professors in computer science or engineering departments. Today, I just want to share with you about the 4 problems we look at before. So the first one, we just look at the microgrids training. So for microgrids, by the name, that's many size power grids. So some power grids, the small size, many microgrids, maybe they produce more power than they are able to consume, so they can sell those energy. And some microgrids, maybe they cannot consume all of the shortable power, so they need to buy either from main power grid or from nearby microgrids So if they do the training between them, that can maybe with lots of advantages. That's the first problem we want to look at. The second one we want to look at is the wholesale market for the energy. We want to include the demand response participants and the renewable energy sources as determine components in the wholesale market to encourage them to produce more energy, because that's green energy. And the third one, we want to look at the plug-in electric vehicles charging problem. Now, every customer, they want to minimize their cost to charge the vehicle. Of course, there are so many papers, researchers consider this problem. Now, for us, we consider one more constraint put on this optimization problem. When we look at the charging problem, we just look if all of the vehicles charging at the same time, maybe that will increase the burden for the power grid. So maybe that causes lots of problem. So we want to have a strategy. Let the electronic vehicles charging maybe at some different time, and not to exceed the power system to over load. Okay. Now the last one, we consider the economic dispatch or dynamic economic dispatch. This kind of like when we know the demand and we want the power generators or the power providers, they provide sufficient power to satisfy the demand. But meanwhile, we want the sum of the cost for the power generators minimized. Okay, that's a four problem we want to look at. So first one, when we look at the microgrid basically contains kind of like every component for the power grid. Just the size is small. So with some components, they can produce power. Of course, lots of customers, they consume power. For the microgrid, if some of them has more power to sell, but some of them they cannot, they are short of power, they need to buy. Now, if they just do the training in the nearby microgrids, that has can save the loss. So basically reduce the loss when you transfer the power in the power grid, right? If you just transfer the power just a very short distance. The other thing, I think when the microgrids, when they do the training, in general, the price they reach, that's benefits to both sides. For example, if the one microgrid produce more power they can consume, if they sell that to main grid, the price is definitely cheaper if they sell to the nearby microgrids. The other side, if the microgrid to buy the power from the main grid, the price is higher. But if they buy from the nearby microgrid, the price is lower. So that's basically beneficial to both sides. Now, when we look at this training scheme, when we design this model and the strategy, we consider one more kind of like the requirement for the microgrids when they join the training. join the trading. They don't want to disclose their own personal, basically microgrid's own information to other side or even the partner. So we introduce the central unit. We call that market operator. This one just collected the information from all of the participants. So the microgrids between them, in general, they don't disclose their personal information. So they just transform the information with this one. Now to keep the privacy of each participant. When we do the modeling, now the signer, just as the leader, first, they just try to find what's kind of a strategy best to them, okay? Now, to signer in this case, the strategy means how much percentage-wise, in terms of percentage-wise, the available energy they can sell to other microgrids, okay? That's their strategy. Now, they just do the computing, then find what's best to them, then they send such information to the central unit or market operator here. Then the market operator just do the kind of statistics, got the information, and relate to the buyers. Now the buyer receives the information, they just use the algorithm, just compute what's best strategy to the buyers. For buyers, the strategy is what kind of a price they want to buy the energy. Then this process just repeating or iterating, just like this. Then finally, when they find kind of like if they continue to do the repeating process, no advantage, that's kind of reach the stable stage. So just stop, okay? Now for this, for buyer and the seller, what's the best to them? We just use this function to represent this for buyer. So here I just quickly explain to this function. So for buyer, PS, that's the price. If the buyer buy the energy from the main grid. Now CG, that's this buyer, J's buyer, buys the energy from the microgrid, the price. Of course, we can say if the difference is bigger, the buyer feel better, right? So this is higher the function, so feeling better. Now QG, that's the energy they got at this price. This price. So for buyer, the price difference is bigger, and the more energy they got, basically, they feeling better. Okay, so just maximize this function. For now, this function that's for seller. So WI, basically that's the percentage-wise of the energy available to sell. So 1 minus WI, that means times the QI. QI, that's the energy available to sell for J's microgrid. So that means that's the energy keep, that is selling. So if you keep more, you still can have some benefit, but let's take logarithm. So it's better at a higher price, selling more. So RI, that's the revenue. They sell the energy they got. The other, that's constant coefficients related to the system and this trading strategies. Now, when we design the algorithm, basically we use this property and that. So every time we just compute, when we do the process we just mentioned, we just compute this utility function for both. Now we take the average and we find out the best strategy, basically that's for this to maximize the average function, utility function, average one. If we find the best one, then basically that one, that's the best action for this optimization trading problem. Okay, now that's algorithm we design and others. Now here I don't spend that much time on the technical part. Basically this one, we just try to, we call that the reward algorithm. So currently, if I choose a certain strategy, the next time I just increase the percentage-wise for the current choosing one. Of course, we have to reduce other strategy probability. Okay. Now, that's this is a simulation. I just show you the simulation results for this algorithm, considering this optimization problem. Okay, we just did the simulation in this IEEE 37-bus test failure. So in this system, there are 5 microgrids, and 2 microgrids here, they have energy able to sell. Okay, so this available energy to sell, this available. Now this one, the 4 number here, so 0.2 means 20%, that's a strategy. The seller want to sell. Now 24, that's a strategy, they want to sell the available energy. Okay, this 60%, this 8% strategy. And for the buyer, there are 3 microgrids. They need more energy from other microgrids. Now they want to, the first microgrid, this one, it wants to buy the energy at this 3 price, 22 cents, 28 cents, 40 cents. So each price, we call that a strategy. Okay, now this microgrid 3, it has 3 strategy. This microgrid 5. Now this simulation results, we look at here. Now this is a microgrid 1. It has 3 strategies. So this one, that's a horizontal axis, that's a iteration number. Now the vertical line, that's a probability for each strategy you choose. So in the beginning, we just assign each strategy same probability. So basically 33.3% like that for the in the very beginning. But we can see very quickly the automatic learning system, the algorithm just choose the first strategy. Now you can, the first just 100%, kind of like that's a probability chose the first one. So we can say this algorithm very good, very quickly pick the basic strategy. The other similarly we can say. Now this one, that's for the horizontal, that's the number of iterations. The vertical line, that's a average action. Now the action, basically that's each action means the price for the buyer. So there are three. Now, this is the first microgrid. This is the third one, fifth one. So, and the red one, that's Nash equilibrium. So basically this one, we will assume all of the participants, they know the other side strategy. So this case, I can compute, this is not a complicated one. So we can compute to find the basic strategy. Now for the algorithm, because here each participant, they don't know the other side strategy. So they cannot get exactly. So that's so basically the base strategy to buy, that's about 23 cents, a little bit more than that. So we can say for each buyers, they just gradually pick the one strategy closest to the base strategy, 23 cents. Okay. Now, of course, they cannot pick exactly 23 because in their available choice, they don't have this. Like the first microgrid, the basic strategy, that's 22 cents. So they pick 22. Okay. Now, this is the utility. So basically utility function, that's the highest, basically reaches the maximum. That's a basic strategy. So we can say these three buyers gradually reach the maximum for the utility. Okay, so this is the first optimization problem we consider. The second one, we consider the wholesale market for the energy. In general, in the wholesale market, traditional or even right now, most of the grids, I think the traditional power generators are the major one, and they are determining participant, or maybe most of them, they are the unique one to determine the price for in the wholesale market. But in this model, we just want to encourage the renewable energy sources, those components to be one of the participants to determine the energy price, and still including the demand response participants. So encourage them to be part of the whole process. Now, in this model, we put power utility, basically the traditional power generator, as the leader. Now, the other components, renewable energy sources, microgrid, or demand response participant, as the followers. Okay. And in the price harness, we consider two markets. One is the forward market, one is the spot market. Of course, right now in the electricity trading market, we have not considered forward market. But here we just consider in this model, maybe in the future, we can implement this forward market, just like a start market right now. Now, in the forward market, the price for the forward market price is determined by this formula. Now, some of them, those coefficients, basically parameters coming from the previous trading data. Okay, and to determine this, now we just use the neural network to run to decide this. Now, once in the forward market, we determine the price for the energy, suppose after 6 months, now that's the price. Now, for the participant, if we want to trade such amount of energy in the future, suppose 6 months later, then the income in the forward market, definitely that's the price times the quantity they sell, right, in for the market. Same for funnel, all of this. Now, in the spot market, the price determined here. Now, spot market, the different situation, the power generate the amount, and this in certain situations, the power generated by one of the power utility, the traditional one. And that's a price in certain situation. So in the spot market, the price, the income they got, basically that's a price in this particular situation times the quantity they sell. Now the quantity they sell, that's should be the quantity they produce at that time, but it should be minus the amount they already sold several months ago. Okay, so that should be the difference. So the income, that's the price times the difference, okay, of this. Now, the profit should consider the cost produce such an amount of energy. Now the cost here in general for power traditional generators is a quadratic function, okay, and so the income in the spot market, that's a difference of the income minus the cost, and we take the expectation because it's a random variable, right? And for funnel, similarly, is income in the spot market minus the cost. But for funnel in general, the income, the cost is the constant for renewable energy sources. Now, if it's a customer demand response, that's kind of like related to the comfort of feeling. For example, right now the energy price is at this moment is very high. Maybe we want to reduce. Suppose the air conditioning, I just want to make the temperature a little bit lower, or higher. Suppose in summer, then this case, maybe you don't feel comfortable. So this kind of cost, that's kind of like related to the comfortable from the customer. Okay. Now, the main characteristic for the funnels is the uncertainty. So in the forward market, if they want to deliver this amount of energy in the future for the traditional power generator, no problem, they just prepare sufficient material. But for renewable energy sources, for example, wind generator, maybe they cannot produce such energy in the future if the wind turn out no wind at that moment, that day. So that's with uncertainty for the renewable energy in forward market. And we will deal with this. So anyway, the income or profit for both sides, that's kind of like in the forward market plus the spot market, okay, for both. So the optimization problem, basically, we want to find a strategy for the traditional power generators, find the basic strategy, what can maximize their profit. Under that, each funnels, they want to maximize their profit, okay? And finally, we want to address in this modeling the uncertainty from the renewable energy sources. Now, what's the overbidding risk? Just like I mentioned, for the renewable energy sources, suppose right now they sell 50 degrades in after 6 months for one generator, but after 6 months that day no wind, so basically they cannot deliver anything. So we call that overbidding risk. So basically, the spot market, the energy they produce is smaller than the energy they already sold in the forward market before. Okay, so basically this one forward market delivering amount, this in the spot market produced amount. If this is the part, we use this function to represent the risk, overbidding risk. For this one, definitely that's not a benefit. So we want to the renewable energy participants components just try to avoid overbidding risk. So here for the farmers, their profit basically we need to minus their overbidding risk. And the gamma, that's a weight basically. If this coefficient is bigger, means you penalize this overbidding risk more. So if you put this number bigger, basically we can imagine the farmers should try to bid less in forward market. Okay. So in this modeling, the optimization problem coming out like this. So we want to maximize power generator, traditional or farmers. We want all of them, they want to maximize their profit. Now, in this model, when we want to deal with the find the solution, because we have to guarantee it has solution. Here, when we deal with this, theoretically, we just use the sample average approximation to approximate the expectation. Okay, use this one to expect. We use this basically here, this one, to expect this expectation of the random variable. Now, under this transformation, theoretically, we can say under this condition, this optimization problem guarantee it has a solution. And we design algorithm to find the solution. Now, this is just a part of this. I don't go to detail here. Now, I just want to show you. So horizontally, that's a overbidding risk coefficient. Like I said, if gamma, this coefficient is bigger, means we penalize the overbidding component more. Okay, just try to net those components to avoid overbidding risk. Now, I look at the last one first. So gamma as the vertical, that's a overbidding risk. Okay, this coefficient. Now, for the red one, that's a wind energy generator. Now we can say when gamma is bigger, this one, the overbidding risk just becomes smaller, because this is not for overbidding risk. So they just want to reduce the overbidding risk because they penalize becomes more and more. And this sun energy for the yellow one, they will kind of like becomes less. And this one, that's a demand response component. Kind of like doesn't change much for this one. But for the traditional power generator, no overbidding risk, okay? And when we penalize more for overbidding risk, the blue one, that's a traditional power generator. In the forward market, it will bid more and more quantity. And the other with uncertainty components, renewable energy and the customer demand response components, they will bid fewer, okay? Now the clearing price will increase a little bit. So we can expect the profit for the power generator will increase a little bit, the other will decrease. So if we now what's the beta value when we pick is good? Now that's really depends on many analyze. Because for this one, we need to consider the society's totally benefits. Okay, so I don't go much about this. Now this is just compare with other algorithm, the scalability of our proposed algorithm. It's very fast and with better scalability. Now the third one, I just want to look at the PEV charging problem. Now for this one, with more and more PEV go into the road, if like a 10% PEV more in the road, maybe the peak node for the power grid will increase like 18%. So we can think if 20% increase of the PEV on the market, then that's a notable increase for the peak node in the power grid. So we want to consider this problem. Now, we consider suppose the power grid, this feeders capacity. Suppose the capacity for this feeder is this one, PL. Now, I use D representing the non-PV charging, okay? So for the PV charging, the maximum usage should be bounded by this, and this, okay? Otherwise, we are surpass the feeder's capacity. Now, we don't want that happen. So in this optimization problem, we consider this constraint. So basically, the PEV charging anytime don't exceed the power grid's capacity. Okay. Now, the optimization problem is basically minimize the cost of each PEV customer. Okay. Now here, when we use this, that means for any electricity power pricing, we include this very general pricing function. Can be anything you want. Of course, this in general, that's an increasing function for power pricing function here. There's other components. So here, like I said, many people consider this optimization problem. We just consider one more constraints here, okay? Now that's the algorithm we design, and for this, we still from theoretically we get that's much faster than some of the other existing ones. Now, when we use this algorithm to consider the following problem, and when we do the simulation in this bus distribution network here, and we consider the pricing function is like this. This is a piecewise function. Okay, we separate 3 periods the pricing. So this is peak time in the evening from 5 o'clock to 9 o'clock, and after 9 to in the morning 10. That's a lowest part valley time. Okay. We did this for 400 PVs charging. Now, the first one, we consider the PV charging for 400 PV. And here, I want to show you the blue area. That's a basic node vertical, that's a node level, okay. The blue one, that's from non-PV, or we call that's basic power usage. Now, the brown one, that's from PV charging, okay. And the dot line here, that's a power grid or capacity, or the fader limitation or capacity, okay. So definitely this one, we don't consider the faders overload problem, just consider the optimization. Each customer just minimize their cost to charge their PV. Now we can say in this time period, the power usage basically exceed the capacity of the fader. So now this is not good. We don't want this happen because this maybe destroys the power grid, right? The system. So the second one, this one, we consider the faders overload the problem. So basically we want minimize the cost. Meanwhile, don't let the fader or basically overloading. Okay, now we can say this doesn't need overloading for this. If we use this strategy, consider the overload problem. Now that's good. However, in general, because we are putting more constraints, we expect the cost more for customers. That can happen. But for this case, when we did the comparison for the cost, now the red one, that's with the overload control. So basically, every time the customers, when they use the power, don't exceed the power grid's capacity. Now the blue one, that's without considering that problem. So in general, we expect the blue one, the cost is smaller. But we can say with time going, that's kind of like a similar level, okay, the cost. So that means it's very good. We kind of reach that every customer, the cost minimized and the overloading problem resolved. This just compares the speed of the algorithm we proposed and the other common ones. The last one I want to look at is economic dispatch problem. So basically this one means we know the demand. So right now the producers suppose this known customer demand, this demand. Now, PI, that's suppose one factory produce the power. So all of the power generators should produce power just equal to the demand. So that's demand supply balance, same. That's perfect, right? And we want the sum of the cost to produce such a power for those factories, the sum, minimize. Okay, we not just minimize the individual factory, just a sum. Okay, and of course there are some constraints for each factories. Once they produce, there are some the maximum and the minimum power they produce. That's with some constraints like this. So we want to find the optimization problem, the solution for this problem. Now, a very common one, we just converted this problem to multi-agent problem. Basically, we converted to the consensus of a multi-agent problem. Now, what's the incremental cost? So basically, for each factory or generator to produce, suppose one more degree in electricity, how much cost? Suppose one factory is 25 cents, the other one is 20 cents. Okay, now that's an incremental cost. When you increase to produce a unit electricity, the cost we need to take. We can think about simply, if we don't consider other constraints, suppose we don't consider this, we just like this here. If you want to this reaches the sum, reaches the minimum. In general, the incremental cost, if all of the incremental cost is same at that time, kind of like we think you reach the basic solution. For example, just like I mentioned, suppose one factory, the incremental cost is 21 cents, the other one is 25. Now, if we want to have the minimum sum, definitely you want all of the factories, the incremental cost same at that moment reach this. So some of them, they just converted this problem to multi-agent problems, consensus. Consensus means reach the same. That's consensus for multi-agent. Just let the incremental cost reach the same. Now, how do we convert this to a graph, the multi-agent? So basically, every factory, that's kind of like a vertex, one agent. Now, the edges here, we collect those factories. If they can communicate the information each other, then we put one line between them as one edge called in multi-agent system. Okay. So that's what most of work done converted to multi-agent system consensus problem. Okay. Now to do this, to make that in zero, like I said, to reach to consensus, we don't consider this constraint. So how can we convert it to the multi-agent problem without that constraint? We just consider this with the penalty term, this optimization problem. Now for this one, so we consider the following optimization problem. So demand and the supply, same, they satisfy this condition, but we don't have another producing constraints for each factory, but we just put it here, Now, what's the difference between this optimization problem and the original one? We have this result. If the theta basically is very small, then this problem, this one, and the original one basically equivalent. The optimization solution same. So that's the idea. We just convert it to this penalty form, but the net theta very small. This is a algorithm we design. We use the second order algorithm, continuous form. Now, and we designed another algorithm that's a robust one. Now, for this algorithm, this second one, we needed this condition. So basically, initial condition in the very beginning, all of the producers, the initial energy they produce, the sum surely satisfies the demand. That's the requirement. Otherwise, this algorithm cannot reach the optimal solution. So basically, they don't satisfy the demand supply condition. So now, however, for this algorithm, we don't need this condition, okay? So it doesn't matter in the beginning, if the initial condition is not equal to this one, the sum not equal to this, that's fine. Eventually, this dynamic, with time going, the dynamics of this system, this one, will push those behaviors, basic dynamics, toward to the basic solution, and they satisfy this condition, okay? Oh, not this, because it's initial. I mean, with time going, eventually they will satisfy the demand and the supply condition. I just show you quickly the simulation for that second order algorithm. So if we use this function as the cost function, okay? Now the coefficient of this one is given here. Now this is for this system with 5 generators, 5 factories to produce energy. And the one edge, one line here basically means they can communicate the information between them. So that's in terms of graph, that's edge, okay? So basically we convert it to the multi-agent system. Now, here I just show you the 2 pictures for this. The first one, that's a result. Now, the vertical basically, this one, that's a power generated by each generator. There are 5 generators, okay? Maybe not clear in the back. Now, the first one, that's the algorithms by second order we proposed. Now, the second one, that's the one we use the first order algorithm, COM1 used it. So this one, all of them, they will approach to the basic approach to the best solution, the stable states. However, you can see, I think the second order, kind of like after 200, reaches a stable stage. But for the first order, kind of like 400 or more than 400, 500, you kind of reach the stadium states, or maybe 600 out here. So the second order is much faster. And this one, that's a consensus. That's an incremental cost. The vertical one, that's the incremental cost with time going for the 5 generators. Now, the incremental cost, we can say after about 200 or 300 seconds, they kind of like reach the consensus. So like I said, if the system reaches the consensus for the incremental cost, that means the states for the generators, they reach the state-based states. Now, this is for the first order. Now you can see it's kind of like after about 500 or 600 seconds, the incremental cost for this system reaches a consensus. So from this concept, incremental cost, we can tell too it's running much faster. Okay, that's oh, one more. I just look at quickly. I think running out of time. For the dynamic economic dispatch. So basically here we consider more like the problem we just mentioned, dynamic dispatch, but we consider more period. So suppose here every day, suppose H is 24, we consider 24 time period. Each time period we consider the optimization problem we consider a moment ago. So, but for each time period, the demand may be different, right? And each time period we need to satisfy the supply demand balance and satisfy the each generators producing constraints. And there is one more constraint. From one period to next period for each generator, the difference cannot be very big or beyond a certain constraint. That's a change constraint. Okay. Now, if we result this constraints, we don't call this dynamic because that's basically previous economic dispatch problem. You just consider each problem like this independently. That's it. But because of this, we cannot consider independently. So we have to consider this whole as one problem. So we call this dynamic economic dispatch. And the idea, similar, we have to convert it to this problem. Like I said, if a sigma here is very small, very, very small, then the solution you got from this one, but with the one this component, the solution kind of like the same as the original optimization problem. Now, the algorithm we design, here we design 2 algorithms. One is a central algorithm. This central algorithm. Another one is a distributing algorithm. Okay. Now, this simulation results I just share with you. For this one, we have for this system, we have 6 generators, and the period for this dynamic period we consider is 1, 2, 3, 4, 5 periods. Okay, so this power generated for the first one, the horizontal, and that's basically the time. Okay, the time period, each time period, how they evolve to the optimal states. We can say the power produced, and the following one, of course, all of them approach to the best states, and the second one, of course, approach to the best states, stable states very fast. Now you can see The second one approach to the stable states much faster, right? Compared to the first one. First one in here you get the stable states, but this one for first period you just very quickly. Now the second one we use the algorithm we proposed. Now the first one, that's a traditional other algorithm. So this approach to the stable states much faster compared to another traditional ones. Now this showing similar this incremental cost consensus. Okay, we still can. The second one, that's we run the algorithm we propose. Now the first one, that's other traditional algorithm. So this is the one we propose, running faster, much faster to find the stable states. And with this, I finish today's talk. Before I stop to answer your question, I just need to thank my collaborators in this particular field. So as I mentioned in the beginning, basically I have several areas focused. Basically in the very beginning, my area is about neural networks dynamics. Okay, then we just look at other computational and computational intelligence and intelligent control area. And this kind of like the application of the computational intelligence. Thank you all. Thank you.
Thank
Any
you,
questions?
Thank you, Professor Wang, for the informative presentation and multidisciplinary ideas that you have discussed, including many problems in the smart grid, how to do optimization for them by a variety of methods from computational intelligence. The floor will be open for questions. We can start by those who are here first, and then we can take some questions if we have from the audience online. Please feel free to ask Dr. Wan any question or give your feedback on his talk.
Yes.
Thank you very much, Professor Wang, for the great presentation. My question is about the second part, I believe, when you talked about the gamma that sets a parameter for the risk of overbidding. About the overbidding problem. Yep.
Overbidding.
Yes, overbidding. Yes. So the eventually this cost function for an operator or for the market participant, he wants just to maximize the profit, right?
You're right.
Say.
Yes.
So how can we set gamma as a market participant? I mean, I know you changed gamma, you varied gamma, which showed amazing results. But for a market participant in real life, what should I set gamma?
Oh, good question. Basically, this really good question. Even for us, we are still cannot set up or the best gamma for all of the participants. This one we need to consider maybe the social welfare, because basically if the gamma is smaller, that's beneficial to the renewable energy participants. But if we set gamma higher, that's penalize the renewable energy participants, kind of like that. However, if we set gamma is smaller, basically that's we want to encourage the renewable energy participants. But we just worry in this model we consider because for the renewable energy participants, they knew their cost, that's kind of fixed in the very beginning. So suppose they found that the price is good for them, they psychologically, they just want to bid more in the further market because that's determining the price. So if all of the participants bid more, then they can finally deliver such energy. So in the spot market, we are kind of like a short energy because this can maybe cause a problem if all of the participants doing this for renewable energy. End up maybe we have to stop some power grids. We cannot supply the electricity. So that's causing a social problem. So we want to avoid that. The question you raised, that's particularly important. How do we determine this gamma in this model? So that will come another optimization problem. We may need to how to set up the optimization problem. We consider the social welfare inside. Okay, so suppose that part you got a loss, you can get compensated from this part. Thank you.
Thank you. Other questions? Do we have questions from online audience? Huh? Can you go ahead and read? None? Okay.
Since there's no question, it's another topic about multi-agent systems.
Yes.
I saw you did a lot of work on multi-agent system, and you said that it maintains the privacy. You know, if I have a policy that I'm following, you have a policy that you're following. But if we are sharing in a participation, no need for me to share my policy with you, right? Although we can reach a global optimization, a global optima. So do you think while we're trading or while we're communicating, do you think after a long time of communications, multiple communication, I can figure out your policy?
Yeah, that's a great question. So right now, for the multi-agent, for the last part, I just didn't mention because there is one requirement when for the multi-agent to reach the consensus, they have to communicate with not each other, but the whole graph here, kind of like a one agent, suppose one factory, they communicate their information to the other one. Anyway, any of this, once information, any one of them, their information should be reached the other, not directly, but maybe suppose from here to this one, I can reach that from to this point, and here, and here, and here, and here. So there is a definitely condition to reach the consensus. Now, not just the information privacy. They have to be able to communicate any one of this through other agent, so factory. If one of them suppose is isolated, his information cannot reach the other, then definitely cannot reach consensus. Because to reach consensus only when all of them directly or indirectly can communicate, share the information, then they can reach the consensus. Maybe I have not answered your question. Did I answer? Thank you.
Okay, thank you, Professor Wan. And there may be other questions. You can communicate directly with him through his email. Of course, this may, after leaving, could be some collaboration on one. We really appreciate your visit for KFUPM, and we hope you enjoy the rest of the day. Thank you.
Oh, thank you so much. I definitely enjoy the trip. Especially, I hope in the future I have opportunity to visit this great university again. You get the best students here. So I want to say the students and meet this great faculty too in the future. Thank you so much. Thank you. Thank you. Oh, great. Oh, here. Oh.